One thing that isn't mentioned on that packet that you just worked on is some solids do not have a nice, neat structure. These are referred to as amorphous. Glass is a good example of that. And as the second bullet point indicates, if you cool liquids super fast, you do not allow them the time to arrange themselves in a nice, neat, orderly manner. It's playing musical chairs at a walking pace versus a running pace. It's a walking pace, everyone can easily find their chair, except for the one person. But if they're kind of jogging around in the circle, now you have three people diving for the same chair because they don't have time to think. Now, granted, I'm using personification here and atoms aren't actually thinking, but again, they're not allowing time for those attractive forces to really set in. Because what differentiates these solids then that we're going to go over is those attractive forces. And that's why you saw different melting points when you looked at that packet. Different amounts of heat required to make them melt. So these different properties are things that the College Board wants you to be aware of these different types of solids. That being said, we cover this a little bit today and then we move on from there. Because there isn't a lot more beyond what we've just gone over when it deals with these solids. So that's the good news of it, and kind of the bad news that we have to spend part of a day going on this stuff that you'll see a little bit on. Unless you want to go forward for me. All right, so, again, the packet's called the types of solids, but sometimes we refer to it as its crystalline structure. And what holds these things together determines those properties then. So what I have left then is just going over those four types of solids that you went over in that packet. So, ionic. We're going to focus more on ionic with the second half of notes here. But a few things to break down about ionic. Remember, it's a repeating unit of cation and anion. So positive and negative charges attract to one another, left, right, top, bottom, forward, back. That makes that ionic lattice structure. What we are going to go over with the second half of notes here in a little bit is that it depends on the size of the cations and anions and how well they attract one another. As you noticed in the POGO packet that you were working on, melting point is something that's brought up of a property that's very common. Solubility in water is brought up as a very common property. But lastly, the ability to conduct electricity is a very common property. Last unit, we went over electricity, flow of electrons. Now really, electricity is as much about a flow of a charged particle as anything else. So in that third bullet point, when I state that ionic compounds as a solid will not conduct electricity, it's because when ionic compounds are a solid, those ions are in a fixed position. But if you were to melt it, there's now a flow. The ions are free to move about. And that means they're able to carry a charge from point A to point B, thus a flow of electricity. When you dissolve ionic compounds in water, you are also giving them that ability to flow right away. Alex was talking to me up front about that sort of thing of being able to conduct electricity or not. He noticed that in the packet, it mentioned that water is very slightly able to do that sort of thing. There's a reason why that we get into second semester that deals with how water, H2O, isn't actually pure H2O throughout. But tap water in particular has ions already dissolved in it. Heck, both me and Miss Knatz yesterday, when we turned on our sinks for probably the first time in about a week or so, because both Chem and AP Chem haven't been doing labs, we saw that water can dissolve a lot of stuff. Our water was brown for about the first minute and a half of us running the tap yesterday. Then it actually started to clear up a little bit, but you have ions in tap water on a regular basis, so tap water can conduct electricity. That's why they always warn you about having certain things next to running water. Last one. The topic of lattice energy specifically is what we're going to be going over with the second half of notes a little bit, so I'm going to save that one for there. But that's going to lead to what things are held together more tightly. If they're held together more tightly, it takes more energy to pull them apart, higher melting points, things like that. Okay, so ionic, again, we'll focus on a little bit more later. Molecular. Molecular solids is probably what we focused more on in Chem 1. In Chem 1, we talked about what holds one molecule to another. Sometimes these forces are called van der Waals forces. It's unfortunate some textbooks use different terminology than others. I usually refer to it as intermolecular forces. That's what College Board usually refers to it as, partly because then we just abbreviated IMF, intermolecular forces. Again, inter is between two things, just like the WIA is between two different schools when you compete. So London dispersion forces, maybe they've just been called dispersion forces, maybe they're just called London forces. What do they call it in Sun Prairie? What do they call London dispersion forces between nonpolar molecules in Sun Prairie? So they don't even cover it in Sun Prairie. So because they don't know what word to use, because they see so many different terms used for it. And actually, London dispersion forces occur between all things. It's just that it's the only thing that helps keep nonpolars together. Dipole moments due to a dipole-dipole interaction is another type of intermolecular force. And then the one that I know in Chem 1 we focus on more because it deals with water and how unique water is hydrogen bonding. Those three on that secondary bullet point to start off with is what can hold one molecule to another. So one covalent molecule held to another covalent molecule, it's got to be one of those three. And that is not a very strong force. It's nowhere near as strong as a covalent bond. It's nowhere near as strong as an ionic opposite charge subtracting. It's nowhere near as strong as metallic bonds where they have a sea of electrons floating between the nuclei. Because of that, molecular solids, it doesn't take a lot of heat to break them apart to a liquid. That's why I have the melting point is usually under 100 or in that range. They're not very good conductors of electricity because they do not allow a flow of electrons from point A to point B. And I give you a few examples on the bottom. Again, recognition, if it is a nonpolar molecule or a polar molecule, odds are it's a molecular solid. So looking at the formula of things will help you usually identify what type of solid it is. If you're not given the formula and it's more giving you like it's a substance X, first thing I would look at is the melting point. Is the melting point in kind of normal human range? Or is it more in a laboratory range because we have to heat things up ridiculously high to make them melt? That's your best indication because molecular solids are the weakest solids. Molecules exist on our planet as likely to be a solid as a liquid as a gas. You can't say that about ionic compounds. Ionic compounds have to be in the thousands and thousands of degrees Celsius in order to be a gas. Right? Covalent. Covalent are nonmetals held together by covalent bonds over and over again. So what makes a diamond is it's a carbon atom covalently bonded to another carbon atom, to another, over and over and over again. So if you wanted to melt a covalent compound, you are breaking an actual covalent bond, a sharing of electrons between two atoms. It takes a lot of energy to break a covalent bond. A lot more than an intermolecular force like hydrogen bonding or London dispersion forces. And again, these electrons are locked up in that covalent bond, which is why they are not good conductors. Diamond and graphite, typically not what we want to be conducting our electricity. On the polymer packet, silicone was brought up as another example. Silicone, like in solar panels, is the same sort of bonding scheme.
So we use pentolite, which is graphite.
With the electrolysis lab. So we were kind of forcing electrons through pretty hard to make that happen when we hooked it up to our battery. Yeah. We would never make wiring or anything like that out of it. And I don't know if any of you guys actually used your pencil to touch yourself, but you really wouldn't have felt much of anything at all. Not that I would have recommended, because there's definitely guys in the back that would have. Someone heard me say that some were busy talking, so they didn't go up top and ball and make it fun of them. You know, Peter's knees can move. Yeah. Still have no clue what's going on. All right, ready? Last one is metallic. In Chem 1, we focused a little over an entire class period, so parts of 3 class periods is what I usually did, on metallic bonding. The majority of what makes up structures on our planet is due to metallic bonding. That idea that you have delocalized electrons. I believe in Chem 1 we called it the sea of electrons. That you have these nuclei and negative electrons just floating throughout. Metal's very good at conducting heat. If you don't trust me, turn on your stove, put a spoon's one end on it, and grab the other end. After a little while, you will tell that metals are good at conducting heat. Metals are good at conducting electricity. That's why wiring is made out of metals. But because of that sea of electrons, every nucleus is like a cation attracted to these negative electrons floating within. It's very hard to pull them apart and make it into a liquid. So metals have very high melting points. We also used that sea of electrons to explain why metals can be shaped. Like the gooseneck on my faucet here, that curved shape. Metals can be shaped, they can be thinned out because of how well they're held together. Ionic compounds, you can't shape them into something because they break apart. Because if you shift an ionic compound, you can all of a sudden have the cations next to each other and anions next to each other. They repel and fall apart. But in a metal, it's all about these things that are just attracted to the little parts in the middle. Nuclei attracted to the little electrons in the middle. No matter how you shift it, there's always little electrons in the middle. Once we get done with this slide, I'm going over to the second part of notes, which is going to focus more specifically on ionic. And within ionic, I want to focus on some ionic compounds have a higher melting point than others. Some are actually more soluble than others. All of it deals with that idea of lattice energy that I put on that previous slide a little while ago. So, let's go back to the start here. All right. Lucky for you, you do not need to know what simple cubic, face-centered cubic, or body-centered cubic is. Actually, this first slide, if you don't want to jot it down, I have no problem with that at all. I just want to bring up the fact that if you were to look at our textbook, it's going to talk about how there's different ways that things can stack. The old AP standards would have to know these, and not only that, they have to calculate the density of these things as well based upon that. So there's all these formulas they have to do. More or less, different ways things can stack is if you imagine you have atoms and more atoms, they could stack directly on top of each other. Now, if you do that, there's definitely gaps in there. So it's not that tightly packed. So when we talk about the density of substances, bless you, it's really about how tightly packed things are. Now, on the other hand, you can see within the models I'm holding in my hand that what if I stack this in between those? Now they're filling in the spaces a little bit better, and then I can put this next one kind of in the same arrangement of the first one. So they're filling in the holes. There's a lot less space now in between. They can be more tightly packed. So when we talk about how things are more or less dense, it's based upon that arrangement of atoms, of how well they're tightly packed together. Now, think about this. If I had smaller balls here that I showed you with the styrofoam versus bigger ones, the smaller ones should be able to fit in holes better than the bigger ones, right? Because if I had all styrofoam balls that were the size of a baseball stacked, there should be bigger holes in between than if I used marble-sized ones. Similar thing can be said with ionic compounds, that if you look at this picture of NaCl repeating, notice how Na is smaller than Cl. But if Cl minus was smaller as well, we should be able to pack them in even tighter. If Na was bigger, there'd be more space in between. That space in between is what we need to focus on here. An ionic compound is based upon Na plus and Cl minus attracting each other over and over and over again, as this picture demonstrates. If I wanted to melt an ionic compound, I have to undo these attractions to a certain extent. Liquids are still held together, but now there's a flow. They're not in a rigid structure. That's what makes a solid different than a liquid. A gas means there's no attraction at all. Things are just flying around like crazy. Last thing to mention in this slide. I've been trying to be careful to use the word ionic compound. In Chem 1, in particular with mole conversions, we would call things molecules that weren't actually molecules. A molecule is reserved for covalently bonded things. It's just that it's easier in doing mole conversion problems just to refer to the sodium chloride molecule, even though it's not actually a molecule. So we got to be careful with our terminology a little bit more in this class, I would say. All right. Here is the big slide of what I needed to go over with ionic compounds. I actually introduced the term lattice energy to you when we talked about the dissolving of ionic compounds. That sometimes when you dissolve an ionic compound in water, it gives off heat. Sometimes it takes in heat, so exothermic versus endothermic. And it was based upon the lattice energy and the heat of hydration. Lattice energy is referred to how much energy is needed to separate these ions. And as I mentioned in the second bullet point, that then determines this dissolving aspect. In order to determine within different ionic compounds, which is one of the goals that I have for you guys either today or next class, depending upon how much time we have left in class. In order to determine within ionic compounds which ionic compounds will have a higher melting point than others, so which ones are held tighter together, there are two factors that determine how easily it will be for ionic compounds to melt. And those two factors I have on the bottom of the board here. First one's called charged product, which is also based upon what's called a Coulombic attraction or Coulomb's law, that opposite charged particles attract each other. And then the distance between the two ions. Remember when I was holding up the models, bigger models would have more space in between them. Well, if there's a greater space between ions, it should be easier to pull them apart. Smaller space between things should be harder to pull them apart because they're closer together. And when you have two things that are attracted to each other that are closer together, it's harder to pull them apart. Most students have no problem with this second bullet point, that idea of smaller ions. Again, if you use that visual of smaller things can be fit into holes in the crevices better so they're closer together. Smaller things closer together, harder to pull apart. If it's harder to pull apart, that means it would take more energy to do it. Higher melting point. So this one, usually we get big things farther away from each other. So it's a little bit easier to pull them apart. Charged product. What I'm referring to with charged product is that there's a difference between Na+1 and Mg+2. Mg+2 is a higher charge, so it should have a higher level of attraction to a negative thing. So it can be attracted to F-1 a little bit. It can be attracted to O-2 even more. If you've ever noticed, when we did double displacement reactions, when you had that solubility table and there's these S's in the I's, first off, second semester you're going to learn that that's simplification, because any ionic compound can be dissolved in water if you use only a little bit of it. But most of those things that hit the I, the insoluble, were things with +2 charges, +3 charges, -2, -3. Because the greater attraction between opposite charges, the more likely they'll stick together. I mean, alkali metals, Na+, Li+, K+, they never form a precipitate because they're only a +1. They have a little bit of attraction. Nitrate, NO3 -1, never creates a precipitate. However, sulfate, SO4 -2, carbonate, CO3 -2, phosphate, PO4 -3, these things create precipitates because there's a greater amount of charge. And that's what charged product is referring to. The bigger amount of a charge, +2s and +3s, -2s, -3s, are more likely to attract the opposite charge more. Greater attraction, harder to pull it apart. What I'm going to end with here is an example. We could ask you to arrange these 3 ionic compounds in order of melting point. So you started the class with just identifying, hey, metals take a lot of energy to melt them. Ionic compounds take a lot of energy. Covalent takes a ridiculous amount of energy to melt them. But now we can look at subsets of this and look at specific ionic compounds. Beryllium oxide, lithium oxide, and silver oxide. What I would look at this is 2 parts. First, I would look at the size, and then I would also look at the charge. Well, oxygen I know is a -2 for all of these. Silver is a +1. Lithium's a +1. Beryllium's a +2. What I would first notice if I'm trying to arrange these in order of what would be the easiest to melt and the hardest to melt is I would notice that this right here has a greater amount of charge. On the previous slide when I referred to a charged product, if I were to multiply 2 times 2, the charge of this and the charge of that, that gives me a charged product of 4, as opposed to these other 2 only give me a charged product of 2. 1 times 2, 1 times 2. Bigger charges means more attraction. More attraction means more energy is required to break it apart. So based upon what I just shown, I know beryllium oxide is going to have the highest melting point. It's going to be the most attraction. When I look at lithium oxide and silver oxide, they both have the same level of attraction, a 1 and a 2. So now, if you have the same level of attraction, we need to base it upon the size. When ions are closer together, that's a good thing to hold them together. Which one is smaller, lithium or silver? Lithium's smaller, right? Just you can look at the periodic table. I could give you the ionic radius if I wanted to give you numerical value for it, but silver is further down the periodic table and has more shells, it's bigger. So silver oxide has the least attraction. So if I were arranging these in order of melting point, I would have to put the silver oxide first. In fact, I looked up the values. Silver oxide will melt at 280 degrees. I actually have silver oxide in the back room, and with a Bunsen burner, I can heat that enough up to make it decompose into silver and oxygen. So I can actually break apart those attractions with just laboratory equipment. On the other hand, lithium oxide, over 1400 degrees Celsius. Beryllium oxide, over 2500 degrees Celsius. The more attraction is kind of the important thing first. Plus 2s and minus 2s have a greater attraction than plus 1s and minus 2s. But then after that, you also want to compare how small are these things.